So we're going to look at some examples real quick when our derivatives tests fail us to find local extrema and how we can connect that to points of inflection. So let's look at a function that I've defined here, x cubed. So we know from our first derivative test that we could use that first derivative to try to identify some critical points, see where they change sign, and determine where there's maximums and minimums. And in this case, we can tell that there's nothing. So let's go see how we'll get to that point. So if we looked at the first derivative, we could identify a critical point because there is a value where the first derivative is equal to 0. However, we can't apply that first derivative because there is no change in sign. So what we could have done then is we couldn't use our first derivative because we don't have any, like I said, we don't have any change in signs. So we could go look at our second derivative. We talked about the second derivative there is that if we could still identify our critical points using our first derivative, which we did, we could go ahead and just ask ourselves, well, what is the value of the second derivative there? Because that would tell us the shape of the graph. Is it bigger than 0 or is it less than 0? So if we graph the second derivative of that function, the problem is, again at 0, 0, or again at the, I should say the input of 0, the function is exactly equal to 0. So it's not concave up or concave down because it's not bigger than 0 or less than 0. We got to this special little point here where if the first derivative was 0 and the second derivative was 0, then it didn't tell us anything about local extrema. But what it would tell us then is that we can connect that idea to points of inflection. It's not going to give us anything to do with maximums or minimums, but if we run into that situation, maybe it's a point of inflection. And again, if we go back and we look at the original function, we can see that does, in fact, is what happens at x equals 3. X equals 0. So what that we can look for now is if we run into that problem where, again, the first derivative was equal to 0, but we couldn't use it to find any local extrema. So in other words, that second derivative was exactly equal to 0. Because if we could have used the second derivative rule, if it was positive or negative, so we couldn't use that rule means it was exactly equal to 0. Or again, maybe if it was undefined, and we'll see a graphical representation of that. But again, we're just saying, what if we can't use that second derivative test? So what we can look for, though, is where that second derivative is exactly equal to 0 might be a point of inflection. So if that second derivative was 0 or undefined, what we can see is, does our second derivative change signs, whether it be from positive to negative, or whether it be from negative to positive? If it changes signs, then there's going to be a point of inflection. So if we go back to our graph, here's our second derivative. What I am going to do is I'm just going to show it like this, so I can clearly see that at x equals 0, that's where our second derivative changes from the negative values down here in red to the positive values in blue. So because we have found that our second derivative was equal to 0, and the second derivative changed to signs exactly at 0. So in other words, if we thought about our second derivative, the little sign chart here, if we put 0 here, so on this side, the values were negatives, and on this side, the values were positive. So therefore, we can conclude that there's a point of inflection at x equals 0. And again, if we go look at the original function, we label 0, 0. We can, in fact, see that is where we change the point, or where the graph changes inflections. And if it's easier to see, we can go ahead and highlight that on our notes so we can clearly see the concavity is changing from up to down. So we get a picture of that graph in there. So we knew if we kind of copied our number line or our sign chart from before, what we saw was that the second derivative the second derivative changed signs at that value. I'll just get that onto this next page here. So the negative values, we can see that the graph, the original function, is concave down, and then it changes to concave up, right? It might help you to kind of think about seeing how that graph was like a parabola. That'd be a concave up parabola. And on the right one, if I just looked at that, that's like a concave down section of the graph. So we can clearly see then that that's the point of inflection. Another graphical example so we can see sometimes when it's undefined. So let's look at the cubed root of x instead of just x cubed. Let me reset my window here just to a nicer starting point. So if we were going to look for local extrema or something with this function, first we'd look at our first derivative. Now, our first derivative is never actually equal to 0 anywhere. We can see that horizontal asymptote on the x-axis there. What we can see, what I've labeled over here, is that our first derivative is undefined at 0. So that would be a critical point. So 0 is somewhere to look. Unfortunately, we can't use the first derivative test because we can see the values on this side of 0 are all positive, and the values on this side of 0 are also all positive. So we've identified a critical point, but we haven't seen a sign change. So then we could go ahead and look at our second derivative. And now our second derivative, what we see here is there's another critical point here where it's not defined. We can see at x equals 0. It is not defined. So if we're going to try to use the second derivative to prove local extrema, we couldn't determine if that value was positive or negative because it's no value at all. We don't know what the value is. It's undefined. But what we can see is that on this side of the second derivative, that critical point of 0, we can see that all the values were positive. But on this side of the second derivative, all the values were negative. So I don't know the value of the second derivative exactly at 0, so I can't prove any extrema, but because I can see that the second derivative changes from positive values to negative values, I can determine that at x equals 0, there is going to be a point of inflection. And again, if we go back and look at the original function, we can clearly see that at 0, 0 is where it would change from concave up to concave down. Now again, that derivative test won't tell us explicitly if it turns from up to down or down to up. We'd have to just use the second derivative, and we can see that it turns from positive to negative, so therefore it would turn from concave up to concave down. If we flipped the function over or something like that, then we would see that at the second derivative would change from negative to positive, so then the value would change from concave down to concave up. One last example is we won't always be able to have graphs to do this, so it would be important to kind of see this algebraically. So here we're supposed to identify any local extrema and points of inflection on this given function. So there's different ways to calculate the local extrema. So first of all, we'd have to start with our first derivative. So the derivative here will be x squared minus 3. So we need to identify critical points. Now, our first derivative is never going to be undefined. We can square any number, but we can find when is that first derivative going to equal 0. So we'd see here that we'd have critical points at plus or minus the square root of 3. And what we could do to answer the first question, right, if we wanted to prove any local extrema, we could think about a sign chart real fast and put in negative square root of 3 and positive square root of 3. And then do some just quick calculations of the values here. So if I start with something that's less than negative root 3, like negative 10 or something like that, when I square negative 10 and I subtract 3, that is going to come out to be a positive value. Now something in between 0 and negative root 3, I'm going to do like negative 1. When I plug that into my first derivative, that's going to come out to be negative. Then after that, between 0 and positive 3, if I put something like 1 in there, again, my first derivative would come out negative. And then after the square root of 3, if I put in like 5 or 10 or something like that, my first derivative would come out positive. So we have two really great things here. We can see there's a sign change in our first derivative at this point, and there's a sign change in our first derivative at this point. So we could conclude, because our first derivative is equal to 0 at these points. All right, we'll do this one first. So because it's equal to 0 at negative root 3, and the first derivative changes from positive to negative, there will be, so in other words, the graph is going from increasing to decreasing. There is a maximum at x equals negative root 3. Now likewise, we have the same argument for positive root 3, but it's going to be a minimum there. So because the square root evaluated in the function at, the function evaluated at square root of 3 is equal to 0, and the second derivative changes signs. The first derivative changes signs. I can make that more clear. The first derivative changes, and we got to be specific here, from negative to positive. There's going to be a local minimum. So we've identified the first part of the question, and we can do that all using the first derivative. So just kind of making sure we know where that is on the work that we did. This part of the work was just helping us identify local extrema. Now, if we're going to identify any points of inflection, what we would have seen in this first derivative test is that we have this point. We've identified a critical point in x equals 0, but there's no sign change there. So right here at x equals 0, critical point, but no sign change. So that should have been a warning right away. Well, maybe we could use our second derivative test to see if there's some other sort of local extrema or something weird going on. So this would be just logical anyway, but then we could use that to find the points of inflection. So if we go ahead and calculate our second derivative, which I'll do over here. So our second derivative is just going to be 2x. Now, we see here that the second derivative test would fail to give us any information about the function's extrema at x equals 0. Because if I plug in x equals 0, it's exactly equal to 0. There's no comparison about negative or positive there. But what that tells us then is at this point here, the second derivative was equal to 0. So that would be a candidate for a point of inflection, which I'm abbreviating POI. So what we'd have to then do is just look at that sign chart and say, okay, well, what happens on the second derivative before 0 and after 0? And again, in this case, we're working with our second derivative. We know it's exactly equal to 0 right here. But what's happening on this side of the function? And on this side of the function, we can clearly see if we put in a negative number and just multiply that by 2, this will come out to be a negative value. And on the other side, we would have a positive value. So we can make a nice conclusion here. We want to be specific about what we've proven and what we are able to and not able to prove. But what we've said is, and I'm going to write this on the, I can get it all on this page. Maybe I can't. I'll write it wherever I can. So what we've said is, I'll write it on the next page. So because the first derivative at x equals 0 was equal to 0, right? We identified that as our critical point. And the second derivative at 0 was also equal to 0, which is kind of giving us permission that that might be the point of inflection. And then that third rule, and f double prime, so the second derivative, changes signs there must be a point of inflection at x equals 0. And it's always good to go verify all of our results on a graph, right? So we think there's going to be a maximum at negative root 3, a minimum at positive root 3, and a point of inflection at x equals 0. So on this graph here, what we can go see if is that's true. So here's our function, and we can clearly see everything's already labeled for us, that we have a maximum up here at negative root 3. We have a minimum down here at positive root 3, and then we do see the change of inflection clearly from concave down to concave up at x equals 0.